Acids and bases and conjugates. Once upon a time, a young student asked, "What makes an acid and a base?" His teacher replied, "That depends on who you ask." A long, long time ago, a man by the name of Robert Boyle, who all chemistry students know because he invented the relationship between pressure and volume that came to be known as Boyle's law. He studied acids and bases too. Everybody knew that acids taste sour and bases taste bitter, and they also knew that when you mix them together, the sourness and the bitterness went away, and you were left with nothing but salt water. Robert Boyle studied this too, but he never found an answer because chemistry was very young at the time and they didn't have all the information they needed to answer the question. Then, in 1884, a man by the name of Svante Arrhenius took a look at acids and bases, and he came up with a great theory. He found that acids, when you put them into water, give off hydrogen ions, or H+, and bases, when you put them into water, give off OH-. Finally, the reason why acids and bases turn into salt water was answered. The H's come from the acids and mix with the OH's from the bases and make plain ordinary water. And the leftovers from the acids and bases make salt. We can take a look at what makes an acid and a base according to what Arrhenius said. Arrhenius would have called HCl an acid because when it goes into water, it splits into an H and a Cl. So it gives its H to the water. That makes it an acid. NaOH, when you put it into water, the OH is given up to the water, and OH's make NaOH, sodium hydroxide, a base. But he couldn't explain everything. For instance, some things, like plain old baking soda, taste bitter like a base, and they react with acids, but they don't have any OH's, not a single one. So why can't they be explained by Arrhenius? Well, in 1923, two men who didn't know each other and lived in different parts of the world were studying the same thing at the same time. One of them was named Johann Bronsted, and the other was named Thomas Lowry. And even though they didn't know each other, they came up with the same idea at the same time, and even published their work in different journals near the same time. That's why we give them both credit for the discovery, and we call it the Bronsted-Lowry theory of acids and bases. Now, they came up with a theory about acids that was almost the same as Arrhenius. They said that acids give off H+, or hydrogen ions, but they used a fancy new word. They called the H ions protons because they had just been discovered. And they said that acids were proton donors, which sounds really fancy, but it's really the same thing that Arrhenius said with different words. But their definition of bases was a lot different. They said that if acids give off H's, bases must accept H's, and they called them proton acceptors. This was a lot different from what Arrhenius had said, because that meant that things that didn't have any OH's at all could still be bases. Now that didn't make Arrhenius wrong, because his bases, the ones with OHs, they would take H's too. That's what made the water after all. But it meant that things like plain old baking soda, which acted like a base and tasted like a base, could be called a base now. Now remember, Bronsted and Lowry called those hydrogen ions protons, because that was a new fancy word for a hydrogen ion, which is really just a hydrogen atom that lost its electron. So we can look at how Bronsted and Lowry saw acids and bases. If I had an ammonium ion in some water, and one of its H's went away and went to the water, then that would make NH4 ion, the ammonium ion, an acid. Now, if I had some ammonia dissolved in some water, the NH3, and it took an H from somewhere, then that would make it a base, because it would take a H. But remember, Bronsted and Lowry called it a proton, which is the same thing. Now let's look at some whole equations here. If I have HCl and NH3, how can I make the left side look like the right side? Well, if the HCl were to give an H over to the NH3, then the left side and the right side would be the same. Since the HCl is giving up its H, that makes it an acid. And the NH3 taking it, it's a base. How about this one? Cl minus and NH4. Well, Cl minus doesn't have any H's, so it can't give any away. But it could sure take one from NH4, so that would make it the base and NH4 the acid. Did you notice something about those two equations? That's right. They're the same ones forward and backwards. So on the left side, HCl is the acid and NH3 is the base. And on the right side, the Cl minus is the base and the NH4 is the acid. We call these conjugate acid-base pairs. Let's look at how they really act. We have H2SO4 and H2O on the left side. Both of them have H's, but which one is the acid and which one is the base? Well, to find out, we've got to look at the right side and see what can we do to make the left look like the right. Well, if the H2SO4 were to give an H over to the H2O, then it would have one less, and the H2O would have one more. So that would make it look like the right side. So let's do that. The H2SO4 gives one to the water. So if it's the H donor, the proton donor, that makes it the acid. And the H2O, if it takes an H, that makes it the base. Well, you look at that. Water is a base. I'll tell you a secret. Water can be an acid too. It just depends on what it's mixed with. Now on the other side, we started with H2SO4, and it has now one H less. So if it has one H less than what it started with, it's now the conjugate base. So the acid has a conjugate base that differs by only one proton less than what it started with. The base here, the water, it has its very own conjugate acid, which differs by one more proton. So a base, when it gets one more hydrogen, becomes its own conjugate acid. They always come in pairs. An acid has its very own conjugate base, and a base has its very own conjugate acid. So what do we need to remember about these? The first is that they're on opposite sides. If the acid is on the left, its conjugate base is on the right. There are always two pairs, an acid and its conjugate base, and a base and its conjugate acid. An acid and its conjugate base differ by only one proton. The acid, remember, gave one up, so it has just one left when it's a conjugate base. The base differs from its conjugate acid by only one proton too. Remember, the base took one, so its conjugate acid has one more. And the last thing we need to remember is that a strong acid makes a weak conjugate base, and a weak conjugate base makes a strong conjugate acid. Why do you suppose that is? Well, remember, a strong acid is very free with its H's. It likes to give them away, which means that as a conjugate base, it doesn't really want to take them back very much, which is why the strong acid is a weak base. A weak acid, though, doesn't want to give up its hydrogens very much, and if it ever does, it really wants them back, which makes it a strong conjugate base. I'll bet you can guess the same thing about bases, huh? You think a strong base makes a weak conjugate acid? You're right. How about a weak base? That's right, it's got a strong conjugate acid. Very good. Now you know all you need to know about acids and bases and conjugates. Oh my!